This video is over section 12.1. It is an introduction to limits through tables and graphs. In chapter 12, I'm just going to be giving you a very brief introduction to the first major topic that you will see when you move on to Calculus 1, and that major topic is limits. In this section, we will be estimating limits numerically and finding limits from a graph. Here we're going to discuss the informal definition of a limit. So we begin with a function that is defined on an open interval, kind of like this line that is drawn here, this blue line. Now, this notation here, at first sight, is a little overwhelming. I understand that. But this is read the limit of f of x, so the limit of this function, as x approaches c is equal to L. And I'll explain what that means, so don't worry. But basically, if I look at this chart here, what this definition is saying is as the x value is getting closer to c, the function is equal to this number. Now, I know that is overwhelming, but really in layman's terms, what this means is the intended height of a function. So this is like a y value. So we kind of talk about this a little bit more, and there are statements like arbitrarily close or sufficiently close. And those are things that will be discussed further in Calc 1. But ultimately, when you are thinking of a limit, what I want you to think of is the intended height of a function. And the reason we say intended is because the function does not necessarily have to be defined there. For example, in this illustration, we have a hole or an open circle, which means the function is undefined there. However, the limit can still exist. So there are occasions in which a limit exists. So as I mentioned on the previous slide, if the function is undefined, the limit may still exist. And for x values very close to c, the function will be close to that value y. So the closer x gets to c, the closer the function will get to L. Remember this, the intended height of a function. So what we're going to do is we are going to use a table to estimate a limit. And here is your first exposure. So we want to find the limit of 2x minus 2 as x gets closer to 3. So what we're going to do is we are going to make a table of x values that are getting closer and closer and closer to 3. And we are just going to plug those into our function. So maybe we start off with 2.5. If we start with 2.5 and we plug it in here, so plug it in anywhere you see an x, we end up getting a y value of 3. Well, I want this x value to get closer to 3, so let's plug in, say, 2.9. If I plug 2.9 in for x, I get a y value of 3.8. Let's continue to get closer to 3. Plug in 2.99. If that occurs, then we will end up with 3.98. Let's get a little bit closer, 2.999. Well, then the output is 3.998. Now looking at this, I think you can kind of tell what y value we are approaching, or what the intended height is of this function. But let's work from this direction also, just to be sure. Let's start off with an x value of 3.5. If I plug 3.5 into this function, I get 5. Let's plug in 3.01. So we're getting closer to 3. If I do, I get 4.2. Let's plug in 3.0. Oh, sorry, this is 3.1. I apologize. This is 3.01, 4.02, and if I plug in 3.001, then I have 4.002 as the output. As I can see from this chart, as x approaches 3 from the right and from the left, the function is approaching 4. Therefore, the intended height of this function as x approaches 3 is 4. In other words, the limit of 2x minus 2 as x approaches 3 is 4. Now let's look at this graph here. This is the graph of 2x minus 2. And we can see as we are approaching 3 from the left and from the right, the intended height of this function is 4. Therefore, the limit is 4. Now, when you are doing this on your homework, one shortcut would be to plug this function into your calculator, into y1, and then you can either use a table of values, or you can do calculate the value for each one and just plug in x equals 2.5. Then do it again. Calculate the value, x equals 2.9, so on and so forth. That way you are only plugging in the value for x instead of all the keystrokes that it would take in order to plug that in. Just a little shortcut. Okay, let's try this one. So now I have a new function, and I want to find the limit as x approaches 3. So same rules apply. We are going to plug in values that are getting x values that are getting closer and closer to 3. So let's start off with an x value of 2.5. When I plug in 2.5 into this function here, the output is 3. If I plug in 2.9, the output is 3.8. If I plug in 2.99, the output is 3.98. And as you can see, the x value is getting closer and closer to 3. And once again, we can see that this y value is getting closer to 4. Now we're going to do the same type of thing from this direction. I want to plug in, you can pick anything you want. Let's plug in 3.5. If I plug in 3.5, the output is 5. If I plug in 3.1, the output is 4.2. 3.01 is 4.02, and 3.001, the output is 4.002. So we can see this is in fact getting closer to 4. So this limit is equal to 4. Now let's analyze this a little bit closer. The graph of this function is given to us right here. And I want you to notice that this graph is the exact same thing as the graph in the previous problem. However, we have a hole. So what I want you to do is take a look at this function, and let's see if we can simplify this at all. So if I start off with this function, And I factor the numerator. The first thing I'll do is factor out the GCF. And then factor what's remaining. Hopefully you are comfortable with factoring. When I factor that, I have x minus 3 times x minus 1. And you should notice that the x minus 3's cancel. And hopefully from your previous problems, or I'm sorry, your previous math classes, you know that when these factors cancel, you're left with a discontinuity that is a whole. So there is a whole at x equals 3, and sure enough, we have that illustrated here. So this leaves us with 2 times the quantity x minus 1, which is the exact same thing we started with in the previous problem. So we're working towards something that we will see later on in this material. Now, there are occasions in which the limit does not exist. There are 3 situations when a limit does not exist, and they are listed here. The first example of when a limit does not exist is when the function has an unbounded behavior as x approaches c. And this example is shown here. And basically what this means is our function either increases or decreases without bound. And that, if that's the case, the intended height of the function cannot be determined. If we can't determine the intended height of the function, the limit does not exist. The other occasion, or another occasion when the limit does not exist, is when the limit from the left and the limit from the right do not match. I think this is helpful to look at graphically. So if you look at this, if I want to find the limit as x approaches c, which is 3 in this case, the intended height from the right is 2. But the intended height from the left is -2. Since these intended heights are unequal, the limit will not exist. Finally, the last instance in which a limit does not exist is when the function oscillates between 2 fixed values. So this function, as x approaches 0 from the left and from the right, this function oscillates so much that we are unable to tell what the intended height is. Therefore, the limit does not exist. If we complete this table similar to what we did in previous examples, we'll see something interesting. So what I would suggest you do is plug this function into y1, and then plug these given values in and see what happens. So pause the video and give that a try. Okay, hopefully you did try this. I'm just going to fill in this chart with what the values are, and then we'll analyze what happens. Okay, now looking at this, we can see that as x approaches 3 from the left and from the right, we are getting to a very, very, very big number, 1,000,000 in fact. Well, if you keep plugging in values closer and closer and closer to 3, y is just going to be huge. It's going to be bigger and bigger and bigger and bigger. Just because these values are 1,000,000 doesn't mean this is equal to 1,000,000. Okay? In fact, what this means is that our function is unbounded as x approaches 3. So this is a situation where the graph increases from both sides. Therefore, since this goes up forever and ever and ever, this limit does not exist. The limit does not exist. The limit does not exist. Let's look at another example. Let's do the same thing and plug this into your calculator. When you plug these values in for x, you end up with -2, -2, -2, and 2, 2, and 2. This is the situation where, you have some values from the left and values from the right. So this is not the graph of this, but this is what the example looked like when I was showing you. So the intended height from the right is 2. The intended height from the left is -2. Since these are unequal, this limit does not exist. You will be given examples like this, and this is an example of a piecewise function, and we want to identify the limit or the function value at different points. So let's look at this. In this first part here, we want to find the limit of this function as x approaches -2. So -2 is here. When I look at this, I want to make sure that as x approaches 2 from the left, -2 from the left, and x approaches -2 from the right, I want to ensure that those meet up. Even if the function is undefined there, they still meet at the same place. And that intended height is 1. So this limit is equal to 1. Now, in number 2 here, I want to know what that function value is at -2. Well, because there is an open circle there, that means the function is undefined there. And even if the function is undefined at this x value, we can still have a limit there. In number 3, now we want to find the limit as x approaches 2. So when I look at this, as x approaches 2 from the left, the intended height is 1. But as x approaches 2 from the right, the intended height is 2. Since those are unequal, this limit does not exist. However, I can find the function's value at 2, and that's wherever there's a closed circle. So the function is defined here. This ordered pair is 2, 1. So when x is 2, y is 1. So that means this is equal to 1. Finally, if I want to find the limit of the function as x approaches 0, from the left, from the right, the intended height is -3. Let's look at this one here. Same type of problem. So the first thing I want to find is the limit as x approaches -4. Well, looking at this, I can definitely see that there is a jump. If there is a jump, then the limit does not exist. I can still evaluate the function though. When x is -4, wherever the closed circle is where the function's defined. The ordered pairs given to us, when x is -4, y is 1. So this function is equal to 1. The limit as x approaches -1, well, once again, we have a jump, so the limit does not exist. The limit as x approaches 5. Well, here's 5. The intended height from the left and from the right is the same, and that intended height is 2. However, the function, oh, sorry, this is a different number. Okay, so x is 2. If x is equal to 2 and we want to know where the function, what function value is, well, I have a vertical asymptote there, which means the function is undefined at x equals 2. So this is undefined. That concludes this section.